Have you ever wondered how a simple line equation can be used to predict the future? Yes, you have heard that right. A basic line equation, y is equal to mx plus c, the one that we all studied in our school. That line equation can be used as a powerful tool for prediction. Statistically and scientifically, the concept is known as regression. Many people believe that regression is a recent development in machine learning. No, regression existed way before the term machine learning, AI, data science became popular. It is one of the foundational, fundamental algorithm that gave birth to machine learning, data science, and artificial intelligence. Regression was first developed by Sir Francis Galton in the late 19th century. He introduced the idea of regression to the mean while studying the relationship between parents' height and their children's height. And it was his work that laid the foundation of the topic of regression. Later, Sir Francis Galton's idea was mathematically formulated and extended by his colleague, none other than Carl Pearson, who introduced the correlation, coefficients, and further developed the concept of regression. Despite its recent popularity in data science and machine learning, regression is fundamentally a part of statistics, specifically inferential statistics. Understanding regression is critical for anyone working with data. If you are a statistician or someone who has studied statistical tool to make forecasting, mastering regression is essential. Unfortunately, many people have a superficial understanding of it, and that led to poor modeling and poor forecasting. Regression is also heavily tested topic in financial certification like CFA, FRM, and MBA Finance. But again, let me remind you, these complex topics cannot be covered in 30 minutes, and you need to invest a lot of time to understand them in detail. So if you want to be the part of the live session of CFA, fill the form in the description below where we'll cover regression, quantitative analysis, statistical modeling, fixed income, portfolio management, derivative valuation, equity valuation in detail. And please understand, this is not any advertisement. I have seen people struggling in these topics even after doing MBA finance, even after doing CFA and FRM. And that's why we have started these live session directly from the veterans who have hands-on experience on these topic from the industry. However, let's get started with regression. We should always start a topic with the question, what is the objective? That is simply here to find the equation of the line that can predict the future. So in y is equal to mx plus c, we'll have y and x because they are actual data points. And we have to find m the slope and c the coefficient. However, whenever you want to apply the line equation, the one question you must ask, can I apply regression everywhere? If not, then where I can and where I cannot. Where can regression be applied? Regression is suitable for only continuous data. For example, predicting stock prices or return, forecasting economic growth, estimating sales revenue. However, it's not suitable for dichotomous or categorical data, such as yes or no, true or false, binary outcome like 0 and 1. There we will apply logistic regression, which we'll cover in the future videos. And it is also not suitable in predicting where the data is growing exponentially or decreasing exponentially. Mark that properly. We cannot use regression if the data is dichotomous, exponential movement, and if the data has extreme volatility, which is not normal. Before applying regression, it is important to validate certain assumption about your data. Assumption of regression. Until unless these assumptions, which we'll discuss, are not correct, you cannot apply regression or use it for forecasting. What are these assumptions? First, the error term should be normally distributed. The second, the error term mean should be zero with constant variance. Now, what is the error term? This is the error in your prediction because any prediction will not be perfect. It will have errors. Why? Because you don't have the crystal ball to see the future. Third, no multicollinearity should exist between independent variable. No autocorrelation, positive or negative, should be present in the data. Linearity in parameter. I will repeat, linearity in parameters. A lot of students do it wrong. It's not linearity in variables. And we will discuss about these assumptions in the end of the session. But before that, we have to transit ourselves from the old school mathematical equation to nomenclature of advanced statistics. We can't use the form y is equal to mx plus c. In regression, we replace the school nomenclature y is equal to mx plus c with y is equal to beta naught plus beta 1 into x. Here, beta naught is the intercept, beta 1 is the slope coefficient, x is independent variable, and y is dependent variable. Why we are calling them independent and dependent variable? Because we are using x to predict y. So y is dependent on x, but x is not a dependent variable, but an independent variable. And these independent variables should be chosen with a lot of economic rationale. Yes, a lot of economic rationale. For instance, if you want to predict stock price in India, we'll use GDP growth. GDP growth of India, not the GDP growth of Australia. So, here the equation becomes stock price is equal to beta naught plus beta 1 into GDP growth. In this scenario, GDP growth is independent variable, stock price is dependent variable, and beta naught and beta 1 are coefficients. And also, you cannot say that GDP growth is equal to beta naught plus B1 into stock prices. This is incorrect because a single stock in a country cannot predict or can be used to predict the GDP growth, right? That's absurd. Now, we are saying that we know the GDP growth of this quarter, and I want to know the stock price of the next quarter with the help of the line. Now, how I can fit it? Because for constructing the line, we need only 2 points. And here, if you see properly, we have multiple data points. What should I do? Should I keep on twisting the line up and down until unless I get the best fit line? So the challenge is fitting one line to multiple data points. Unlike a line that requires just 2 points, real world data often involves multiple data scattered across a plot. This means a simple straight line won't fit it perfectly. To resolve this, we use the ordinary least square method, OLS. Just before moving further, whatever I'll discuss about OLS is super complex and need extensive attention because only discussing about the topic OLS in depth need at least 2 hours of sessions. So be very attentive. The goal of OLS is to minimize the error in prediction. A mathematical way of saying is that the goal of OLS is to minimize the distance between the observed actual data point and the predicted data point. Let's understand it properly. Assume this is my scatter plot or different data point of GDP growth and stock prices, where stock prices is on y axis and GDP growth on x axis. Now I'll try to fit a line based on my gut feeling and assume this green line is the best fit line. But how should be the mathematical approach to fit the line, not a gut feeling? Think. I would highly recommend to pause the video and think this question how mathematically you will fit this line. The only intuitive and mathematical answer is that you will try to fit the line in such a way that every point is close to the line. But why are you doing that? The answer is simple to minimize the error in prediction. Now, what this line represent? This line represent the predicted value through the line. What does that mean? Assume the equation of the best fit line is y is equal to 0.2 plus 3 into x. And for say x equal to 4, then the stock price based on this line will be 12.2, right? But the actual stock price came to 15.2. So this is error in prediction. So the error in prediction is 3 and you want to minimize the error, or you can say you want to minimize the distance between the actual y denoted by y and predicted y value on the line, always denoted by y hat. Yes, y with a hat. And you don't want to minimize it for one data point, but all the data points. So you will write summation of all the distances should be minimized, or summation of all the errors to be minimized. But you can see some data points are above, some are below. So it is possible that the summation of the distances comes to 0. Then how will you minimize? Think. So the best solution is to do the square, which will help in three ways. First, it changes the negative distances to positive. Second, it penalizes more distances by squaring it. Higher the distance, higher the weight. Third, getting an easy convex function for differentiation. This is tough. This is complex. So we'll understand it in a minute. So, summation of squared error, in short, is called as SSE. So, we are trying to minimize SSE. Repeating, minimizing sum of error squared or sum of squared error. Let's understand with a lot of attention because this is complex and difficult for many to understand. First, when you say minimize sum of squared error, in this term, you only know y and x, but you don't know beta naught and beta 1. So, how would you know the minimum point or the minimum error value? For that, you need differentiation. But how you know that differentiation will help you in providing the minimum of error squared? Because if you remember, the graph of any squared entity like y square, k square, x square, e square is a convex graph like this, a convex symmetric graph. And what is the slope at the lowest point? That is 0. What is slope of differentiation of e square? Or what is slope of e square at the minimum point? Or what is the differentiation of e square at minimum point? That is also 0. So when you do differentiation of error square and equate it to 0, at the end you will get this. You will find beta naught is equal to covariance of y and x divided by variance of x. And beta naught based on the second assumption will come as beta naught is equal to y mean minus beta 1 into x mean. And this is how you get the intercept and slope, your beta naught and beta 1. But just letting you know that we can only cover the detailed math of multiple linear equation in the live session. This derivation is still valid. We need differentiation in the multiple regression, but the formula will slightly be changed because you should start working in the space of matrix, where the final answer for beta will come as covariance of y and x divided by covariance of x, which will give you the matrix of all the beta in multiple regression. I know this was complex, so pause the video and re-watch this section of OLS till you understand it fully. So now you got the slope, you got the intercept of the line, now you can predict the future. So does it mean that we can use the line equation and we are good to go? The answer is no. So you need to evaluate the model as a new line. Is it even worth a try? Should you even use the model? Should you even use the line for forecasting? How mathematically sure you can be to use the model to predict the future? What tools we have to understand if we can use the model or not? To test the model, we have two simple ways. There are many, but these two will work fine. One is R square and another is F test. R square simply explain the predictive power of the model. R square simply means how much is the variability of the dependent variable is explained by the independent variable. And please note, it is not that how much independent variable is able to predict the dependent variable. No, it is how much variability independent variable is able to explain for the dependent variable. Don't do this mistake in interviews. So if you see the graph, then this section where we have y actual minus y mean and whole square is loosely total variability of y. That is loosely the variance of y. And in correct exact term, it is called as total sum of square. And if you see the graph, then the section where we have y predicted minus y mean square is the predicted variability of y or the variability of y hat. And in correct exact term, it is called as explained sum of square. And because of the definition of r square, the r square formula is loosely explained variability in the y divided by the total variability of y. And the actual formula is explained sum of square divided by the total sum of square. So if r square of your model is 0.80, that means the model or the line can be able to explain 80% of variability in y. Now this r square can also be used to compare between different models. So assume you created another model where you're trying to predict the stock price with interest rate, not GDP, and you want to choose between the two model. What should you do? Then you simply choose the model with higher R square. Now other way to test is to do F test on the model, where hypothesis testing would look like H null, all the beta coefficient is equal to 0, and H alternate, any one of them is equal to 0. We won't go into the detail of F-test as I haven't discussed in our channel that how to perform a hypothesis testing. But for the timing, please just keep in mind that F-test is one of the interesting test for your model and very important test for your model. But R square and F test is not the end. You have to check more. And specifically, if your regression model assumption holds true or not. So, test your assumption. Yes, you need to test all the regression assumption and specifically these three. These three are non negotiable. And let me tell you, I have seen people implementing these model without testing these assumptions and failing brutally in real life. First, error term should have constant variance, which mean it should be homoscedastic. There should not be any serial autocorrelation in error term. And the last, the independent variable should not have multicollinearity. Now, how to test them? The best approach is plotting. You can identify these issues just with plotting. Let's start with the first assumption of homoscedasticity of error. What if it is heteroscedastic? What is the meaning of heteroscedastic? Hetero refers to non-constant and scedastic stands for variance. Now we want constant variance and don't want non-constant variance of error. So do this. Plot error for different x values. So the first plotting is about the constant variance, where error is equally distributed for all values of x. But in the second, error distribution is increasing as x increases. That means conditional heteroscedasticity. Why conditional? Because the error variance is increasing as x increases. Now the opposite can also happen, where error is decreasing as x increases. Both the scenario refers to conditional heteroscedasticity where error variance is conditioned to x, and that's why it is called as conditional heteroscedasticity. Now the third graph is a scenario where the error is not equally distributed for all x but sometime increasing, sometime decreasing, and that is called as unconditional heteroscedasticity because the variance is not constant but it is not conditioned on anything. Now, if your model has heteroscedasticity, then you can't use the model. You have to fix it. But there are scenarios where these graph can fool you and may not be telling you the truth, whether the error term is homoscedastic or not. In those scenarios, we need to use proper statistics tests, proper statistics hypothesis testing to test heteroscedasticity. And in this case, the famous BP test, Brosh-Pagan test, to be used. However, we can only discuss how to perform this test and fix for these issues of heteroscedasticity in the live session. Now, moving to the second assumption, auto-serial correlation. That means that error term should not be related to the previous error term. Now, again, to identify correlation, we'll use plotting. Now, if you see these two graphs, then the first graph on the left is explaining positive serial autocorrelation, and the right one is explaining the negative serial autocorrelation. So, in both the graph, we plotted error in the prediction along with the regression line. In the first graph, error is above and it will remain above the line. And if it is suddenly goes below the regression line, then it will remain below the regression line, which highlights error terms behave exactly how the previous error term is behaving. So we'll call it as positive serial autocorrelation. And in the second graph, if the error is above, in the next instance, the error will be below. And if it is below, then in the next instance, it will be above, which highlights error term is behaving quite opposite to the previous instance, which we call as negative serial correlation. Now, again, these plotting can fool you if you don't have a seasoned eye, have some experience. So, for that, you need to use the famous DW test, Durbin Watson test. Again, we cannot discuss because we haven't discussed hypothesis testing in our channel. Now, the last test is the test of multicollinearity. Now, this test is only valid if you have multiple variable to predict your dependent variable. Like in our example, we had GDP. What if there is GDP and interest rate to predict the stock price? Now, if there is excessive correlation between these two variables, GDP and interest rate, then we need to perform the test of multicollinearity. Otherwise, it will rupture the model brutally. For this, you can apply or simply calculate correlation between the independent variable, your GDP and interest rate, and if the correlation is greater than say 0.5, then you can't use the model. There is another matrix very famously known as VIF to test if there is multicollinearity. Now, if you have tested these assumptions, your model passed these assumption test. Now, you're good to go. And you can use the simple line equation y is equal to mx plus c to predict the future and perform forecasting. But again, you need to do back testing. Now, what is backtesting? What is VIF? What is BP test? What is Durbin Watson test? How to do multiple regression modeling? How we differentiate the SSC and OLS? If you're interested in learning, then please enroll for CFA for live session. We are starting the session by the first week of February. I know I haven't covered a lot of topic in depth today, which I should, but understand only to cover the testing of assumptions need hours and hours of live session. So if you're interested in all those topics, please enroll in the live session. The link is in description below. Thank you. Have a nice day.